Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1967 Stephen Hawking, Roger Penrose, The Singularities of Gravitational Collapse and Cosmology. This essay undertakes a rigorous examination of the seminal paper by Stephen Hawking and Roger Penrose, published in 1967 and investigating the singularities inherent in gravitational collapse and cosmology. The objective is to provide a meticulous, section-by-section analysis, concentrating on the claims, arguments, methodological approaches, and logical coherence of the work. We will adhere closely to the internal structure of the paper, evaluating how Hawking and Penrose constructed their arguments, the assumptions they embraced, and the implications of their conclusions. External considerations, such as the paper's historical context and subsequent reception, will be addressed solely insofar as they illuminate the interpretation and validity of the central claims presented within each section. Section 1: Introduction and Preliminaries. The introductory section of Hawking and Penrose's paper lays the groundwork, establishing the cosmological and astrophysical setting for investigation. The focus is on theorems regarding spacetime singularities, which are regions where the known laws of physics, including general relativity, break down. The initial claims center around the expectation that such singularities would occur in physical, realistic scenarios, which is a striking departure from the prevalent, somewhat optimistic view that a theory of everything might completely avoid singularities. The authors assert the presence of singularities within models of gravitational collapse and in cosmological models representing the universe's origins. This claim is crucial, as it suggests that gravitational collapse, with its inevitable endpoint, is a fundamental feature of the cosmos. The introductory exposition also outlines the key mathematical formalisms, including the concept of trapped surfaces, the use of null geodesics, and the significance of the energy conditions, which are crucial for the arguments that succeed. The emphasis is on establishing the necessary mathematical tools for the proofs that would follow. The authors introduce the initial assumptions, such as the global hyperbolicity and the use of a Lorentzian manifold, which provides the backdrop for the subsequent theorems. The introduction is carefully crafted to present the central thesis that singularities are pervasive in the universe and that this conclusion is a direct consequence of general relativity coupled with physically plausible assumptions about the nature of matter. Section 2: The definition of a singularity. The authors delve into the nuanced definition of a singularity. The claim here is that a singularity is not merely a point where the curvature of spacetime becomes infinite, but rather a deeper structural feature. They offer a very precise definition. A singularity is a geodesic incompleteness. A geodesic is a path in spacetime that a freely falling object would follow, and being incomplete means the path cannot be extended indefinitely. In the work, a singularity emerges when these geodesics end, which means either that they have a finite range of proper time or that some physical quantity, such as density, volume, or curvature, becomes infinite. Hawking and Penrose argue that this definition is more general and simply pointing to the infinite curvature, encompassing a wider variety of scenarios, and avoiding some of the limitations inherent in the prior approaches to the concept of a singularity. The authors elaborate on the importance of identifying geodesic incompleteness to provide assurance that, at the singularity, the spacetime ceases to be well defined and therefore the usual physical laws no longer apply. This rigorous definition is essential for their subsequent theorems, and they defend it by arguing that it provides a criterion that is independent of the choice of the coordinate systems used to represent spacetime. Section 3: The theorem on gravitational collapse. This section represents the most significant result of the Hawking and Penrose paper. The core claim is that a singularity must arise from the gravitational collapse of a massive object under very general conditions. Hawking and Penrose demonstrate this without making any assumptions about spherical symmetry, which was the typical assumption in previous investigations. The theorem relies on several key ingredients: the existence of a trapped surface, the validity of the energy conditions, and the assumption that the spacetime is globally hyperbolic. A trapped surface is a region where light rays emitted from the surface converge inward, indicating that gravity is so strong that the emitted light cannot escape. The energy conditions are mathematical statements about the distribution of energy and momentum, typically requiring that the local energy density be positive or, at the very least, that the energy density plus the pressure is positive at all points in spacetime. The theorem demonstrates that the formation of a trapped surface, combined with a plausible energy condition, necessarily leads to the development of a singularity. The proof involves several steps. First, the authors show that if a trapped surface forms, then it must evolve into a region where the gravitational effects are increasingly strong. Second, they investigate the behavior of the geodesics in that region and prove that, under the stated conditions, the geodesics become incomplete, meaning that a singularity must develop. This is a major achievement, providing a powerful argument for the inevitability of singularities under quite general conditions that can be readily seen in various astrophysical settings. Section 4. The theorem on the expanding universe. Following the theorem concerning gravitational collapse, the authors extend their argument to cosmology. The core claim here is that, under similar conditions, the early universe must have started with a singularity. The main ingredients of the earlier theorem are present, except that the conditions concerning energy conditions and a space-time that is now expanding, rather than collapsing. The crucial concept here is that of a path-directed trapped surface. The proof resembles the one in section 3, but now it proceeds backward in time. The authors show that under the stated conditions, if the universe is expanding and the energy conditions are satisfied, one can trace the geodesics back in time and prove that they must eventually terminate at a singularity. The paper uses the observed expansion of the universe as one of the main ingredients, is present, and they argue that, based on this evidence, it is difficult to avoid the existence of a singularity at the origin of the cosmos. This cosmological singularity is the very beginning of the universe, and it represents a breakdown of our present understanding of physics. Section 5. The energy conditions. The authors then turn the focus to the critical role of the energy conditions within the theorems. The central claim is that the energy conditions are physically plausible under many realistic circumstances. These energy conditions are mathematical statements that encapsulate the properties of the matter and energy content of spacetime. The paper focuses precisely on the weak energy condition, the null energy condition, and the strong energy condition. The weak energy condition asserts the energy density is always non-negative, and the strong energy condition that the energy density plus 3 times the pressure is always non-negative. Hawking and Penrose acknowledge that these conditions might not be universally valid, especially near singularities, where extreme physical conditions might exist. However, they emphasize that within the regions of physical interest in either gravitational collapse or in cosmological development, the energy conditions appear to be reasonable approximations of physical reality. They discuss the connection between the energy conditions with the known physical laws and the behavior of matter. The examination of the energy conditions also considers how they are tested through observation, making their arguments even stronger for the validity of the core theorems. The ultimate aim is to strengthen their argument that the energy conditions, as stated, hold under physical conditions, leading to the presence of singularities. Section 6. Concluding remarks. The concluding section of the paper summarizes the key findings and highlights the implications of the work. The authors reiterate that they have proven, under very general assumptions, that singularities must arise in both gravitational collapse and cosmology. They reiterate the significance of the theorems by showing their interdependence with respect to the symmetries. The implications of the results are far-reaching. First, the theorems challenge the classical physics concept of continuous, smooth spacetime. Second, the theorems suggest that general relativity, within the domain of validity, must break down at the singularities. This breakdown suggests that the laws of physics, as we currently understand them, require some kind of modification to account for the extreme conditions near the singularities. The authors conclude by drawing attention to the incompleteness of general relativity when faced with singularities, noting that the resolution of this issue must await a theory able to provide a unified description of gravity and quantum mechanics. The paper ends on a cautious note, acknowledging the limits of the current theory, while simultaneously emphasizing the very real importance of the discovery. Overall evaluation of the work's claims. Hawking and Penrose's 1967 paper, The Singularities of Gravitational Collapse and Cosmology, constitutes a groundbreaking contribution, initiating a profound shift in the understanding of spacetime and gravity. The central claims, the rigorous mathematical proofs concerning the inevitability of singularities within general relativity, are not merely provocative but also extraordinarily robust. The authors successfully demonstrate that singularities are an intrinsic feature of gravitational collapse and the Big Bang cosmology, independent of highly specific assumptions. This is a critical point. Prior to this work, the expectation was that singularities might be a product of simplifying assumptions, the result of idealized models, or even an artifact of the coordinate systems. The authors, however, convincingly proved that they are inevitable features of relativistic spacetime. The methodological approach, based on the rigorous use of general relativity and the systematic exploitation of the principles of differential geometry, is exemplary. Their use of global techniques, such as the concept of geodesic incompleteness and the exploration of the global structure of spacetime, provides a deeper understanding than purely local analyses. The author's careful definition of a singularity clarifies the nature of these pathological points, showing that the incompleteness of the geodesics, not just an infinite value of the curvature, represents a fundamental breakdown of spacetime properties. The proofs are remarkable. The use of a trapped surface as a gateway to a singularity is a creative and powerful way to avoid the need for spherical symmetry. The theorems are based on the energy conditions, which are often viewed as abstract mathematical assumptions. However, the authors address this concern by explaining the physical plausibility of these conditions and their connection to the behavior of matter and energy. While the energy conditions could be regarded by some as an area that is open to criticism, the authors provide a persuasive argument that, under many realistic conditions, the assumptions are suitable, or at least within boundaries that can be reasonably in. The internal coherence of the arguments is impeccable. The authors take great care to build up the argument step by step, setting the stage with well-defined concepts, then demonstrating the key theorems. The paper is a model of logical clarity. The conclusion, by acknowledging the limitations of general relativity and highlighting the need for a theory of quantum gravity, has proven far-sighted. The work's impact on the field is undeniable. The paper has fundamentally changed the way physicists think about gravity, spacetime, and the origin of the universe. The theorems inspired decades of research into the nature of singularities, the evolution of black holes, and the development of theories that attempt to resolve the singularities in general relativity. The paper's influence extends beyond physics. It sparked debates in philosophy concerning the nature of time, the origin of the universe, and even the possibility of time travel. The work established a solid basis for later investigations. For instance, the theorems provided the foundation for Penrose's cosmic censorship hypothesis, which posits that singularities are always hidden behind event horizons, an idea that continues to be investigated today. It also informed Hawking's own later work on black hole evaporation and the information paradox, further demonstrating the far-reaching consequences of their theorems. The authors recognized that general relativity is not the final word on the topic. Their work showed that the theory is incomplete and it pointed to the need for a deeper theory that would unify gravity with quantum mechanics. The reception of the paper was overwhelmingly positive. The originality and the significance of the theorems were immediately apparent to the scientific community. The paper was quickly recognized as a landmark achievement, fundamentally changing the direction of research in general relativity. The paper's contribution is found also in its ability to stimulate innovation, since the theorems provided a clear direction for investigating the issues concerning the origin of the universe. The impact of the work is also evident in its lasting influence on cosmology and black hole physics. The initial criticisms of the work related predominantly to the interpretation and the scope of its claims, especially the implications concerning the early universe. Some researchers expressed concerns about the applicability of general relativity at the very beginning of the universe, where quantum effects were expected to be significant. However, these criticisms did not undermine the validity of the theorems themselves. Instead, they prompted further investigation into the quantum mechanical nature of the early universe and the implications of the theorems in this regime. The work has also been subject to significant revision and extension over time. Subsequent research has focused on refining the details of the theorems, relaxing some of the initial assumptions, and exploring the implications of the theorems in various cosmological settings. The authors themselves have continued to improve, refine, and extend their work, adding further corroborating evidence for their initial claims. The research into the behavior of singularities has continued, but the core theorems established in this 1967 paper have remained relevant and foundational. In summary, the 1967 paper on singularities, I. Hawking and Penrose stands as a monument to the power of theoretical physics. The authors, with a deep understanding of general relativity and a clear methodological approach, were able to prove that singularities are a central feature of general relativity. The paper remains a landmark achievement that, through its clarity, rigor, and breadth of vision, transformed our understanding of spacetime, gravity, and the universe. The theorems remain pivotal, shaping the direction of research and providing a framework for understanding the fundamental nature of the cosmos. The work continues to drive scientific progress.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.